Hi everyone, thanks a lot for the invitation. It's too bad I cannot come in person, but I hope to do that soon. Can you see my slides here, or?
No, you need to share it again. Now we can see it.
Okay, yeah, so I'm delighted to present this joint work with Olivier Wang on dynamic oligopoly and price stickiness. And so the question we're asking in this paper is really simple, is how to best model imperfect competition in macro, and in particular to study monetary economics. So once you have a dynamic response of the economy to macro shocks. And so far, the literature and in macro and other fields has been using this very powerful and tractable framework of monopolistic competition, where you assume that there is a continuum of firms. So each firm is really small, and each firm doesn't have any impact on what's happening to the aggregate by itself. And so this model is amazingly simple, and so that's why it's been used everywhere: trade, growth, macro, in static cases, in dynamic settings, and in particular as the backbone of the new Keynesian model. And so today what we want to do is revisit this assumption of having a continuum of a very large number of firms, and incorporate the possibility of having only a finite number of potentially really large firms in some sectors. And we think it's more realistic. Now it's also more complicated, but we're going to try to come up with a model that makes it tractable. And in doing so, we're following the ILO literature that has evolved beyond monopolistic competition in a lot of cases, and highlighted all the departures. And so what we want to do in terms of macro is look at whether this changes things. And we think it's really important to do that right now because of the recent trends that have been noted in market power, broadly speaking. So there are stylized facts about rising markups, rising concentration in a lot of sectors, the emergence of superstar firms, or really large firms, that potentially may have a lot of pricing power and act very strategically in the way they price their different products. And so IO focuses a lot on this, on what kind of pricing strategy firms can use to affect their competitors. And we want to see what this implies for how monetary shocks affect the behavior, the response of prices by these potentially large firms, and therefore inflation, and therefore the real effects of monetary policy. So we know that monetary policy affects partly inflation, partly output. And by understanding how inflation reacts in a world with oligopolistic competition, we can understand better how aggregate output will react as well. And so this paper is going to take a very plain vanilla macro model. So we're focusing on what happens to firms when you have imperfect competition modeled this way. And so for all the rest of the economy, we're going to stay as basic as possible, as simple as possible. So on the consumer side, we're just going to have a standard rep agent, infinite horizon, valuing consumption, labor, and money. To model nominal rigidities, we're going to go with Calvo. So that's, we think, it's still the benchmark of the literature, especially the DSG literature. And so we want to depart as little as possible from this benchmark, because we think it's a good first step to understand if you keep that structure and just add oligopoly, what's going to change. Now, we think there are a lot of interesting things to do once you understand that well, to go beyond that once you add state-dependent pricing, because these things could depend on the market structure as well. But today we're going to start with Calvo, and also, like, although it's very much research in progress, recently there's been a lot of advances that show that, in order to match realistic features of the price change distribution, it's important to have features of the menu cost model that make it more like Calvo. So we think Calvo is a good benchmark for all these reasons. And so these were the standard ingredients. What are we going to change? So in each sector of the economy, instead of having an infinite number of firms, we're going to have any finite number of firms. So that could be very large. And in the limit, as n goes to infinity, you go to monopolistic competition. That could be small, potentially having duopolies, or just 3-5 firms, depending on the sector. So that's the main departure. The second departure, that's not as obvious as from the title, is that we're going to allow for a very general demand structure, so very general preferences. So in models of oligopoly, static models or dynamic models, usually they rely on a CS or nested CS structure for tractability. But here it's actually going to be important to go beyond CS. So we're going to use Kimball aggregators. Actually, the paper is even more general than that. Really, any homothetic preferences is going to work. And the reason is twofold. First, once we calibrate the model, try to calibrate some kind of micro evidence to discipline how oligopoly changes the demand structure of the economy, it's going to be important to go beyond CS in order to match the evidence that we're targeting. So that's evidence on the pass-through of idiosyncratic cost shocks, like exchange rate shocks, to firm prices, and the heterogeneity of this pass-through across small and large firms. And we're going to see that you have to go beyond CS to match that. And this is going to have implications for then our calibration and our results on monetary policy transmission. As second, when we explore the mechanism, it's going to be very important to try to disentangle as much as possible what's happening when you change the number of firms, when you go from monopolistic competition to oligopoly, because you're changing many, many things at the same time when you change the number of firms. If you start from a model with some fixed preferences, you're changing the shape of residual demand as you change the number of firms. You're changing the strategic interaction between the firms because they internalize that, oh, there are not that many firms in the sector, in the industry, so they have some power to manipulate the pricing of their rivals. And that's as I said, that's the focus of a lot of work in I/O, in theoretical and empirical I/O. And so because of that, Kimball preferences are going to allow us to decouple, disentangle these different effects in a very nice way. And so working with that, with the structure, we're going to have four main sets of results. So first, I'm going to show you sufficient statistics for the response of the economy, the aggregate response, so response of aggregate GDP, aggregate inflation to monetary shocks. And that is going to be expressed as a simple formula of sufficient statistics that can be estimated at the micro level. So we're going to have a mapping from what happens to the micro, what you observe when you're in a steady state, so you don't have shocks, you observe some cross-sector distribution of markups, elasticities, and so on. And going from that, we can back out what would happen in a transition, so the transitional dynamics in response to monetary shocks. So it's going to be a nice mapping from micro to macro with some sufficient statistics. And if you know these, if you can estimate these, and it may be hard or not, that's an empirical question about the methods in I/O to estimate markups, for instance. If you believe these and you have enough data and seeing how this evolves over time, you can just plug in this formula and say, okay, monetary policy transmission is evolving that way, or I can explain the changes in the transmission because of the changes in these statistics. Now, second, we're going to go beyond that because it's still a lot to estimate, and we don't have these, time varying estimates of these different things. So then we can go take a more conventional route and just solve the model, calibrate the model, and perform counterfactual experiments that would tell you how these statistics evolve if you change things. For instance, if you change concentration, if you have a rise in concentration, fewer firms, larger firms. And so that's going to be our main experiment. And we're going to show you that based on this calibration that targets the most recent evidence on pass-through heterogeneity across small and large firms, so pass-through of idiosyncratic cost shocks to prices, we can back out what happens to the pass-through of aggregate shocks, monetary shocks that affect all the firms, not just a single firm. And we find that concentration significantly amplifies the transmission of monetary policy. So monetary policy becomes more powerful in a more concentrated economy. Now, third, we're going to inspect why. Why is this happening? Why is concentration having this effect? As I said, when you change concentration, you're changing many things at the same time. And so we're going to use this Kimball demand to disentangle the different forces. So this is going to become clearer after you see the model. And doing that, we're going to find that for these kind of shocks, the monetary shocks that are the focus of this monetary literature for good reasons, like they're tractable, they're well understood. Most of the action is actually going to come from changes in the shape of residual demand. So concentration is changing properties of demand like elasticities, or higher order properties like super elasticities, the elasticity of the elasticity, in a way that amplifies monetary policy. Now there are a few other things going on, but that's going to be the main driver. Now fourth, we want to generalize the model to allow for more general shocks, not just these monetary shocks, and kind of embed our structure into standard DSG model, for instance, a New-Keynesian model with an IS curve, a Taylor rule for monetary policy, and so on. And that's going to be mapping, more general path of shocks. So then you can consider interest rate shocks, real shocks, so demand or supply shocks, cost push shocks, and see what they imply for inflation and output. And we find doing that actually, once you allow for more general shocks, so we're going to, the Phillips curve is going to be much more complex than what you have usually, featuring inflation persistence and endogenous cost push shocks. And these things all come from these strategic interactions. And that now concentration has an effect both working through the demand side, changing the demand structure, but also through these strategic effects that I'm going to explain more in detail. Okay, so briefly on the literature. So as I said, like most of the macro work has been built on monopolistic competition. So there aren't that many papers that look at oligopolistic competition and its implication, that looks at non-atomistic strategic firms. So there's some early work by Rothenberg, Saloner, Rothenberg, Rutherford that relied on super games, so repeated games where you have these trigger strategies with some strong results. We're going to follow more the recent IO literature going with Markov equilibria, which are less extreme, and also, incorporate nominal rigidities, because these papers were before the New Keynesian revolution in a way, by the same people, but before, really started to emphasize nominal rigidities. And so we're going to combine these two. Now, a recent paper that really inspired us and has a very complementary approach is by Simon Mongi. So this is more quantitative work. He considers two firms with menu costs, so not Calvo, focusing on menu cost and idiosyncratic shocks. And so using some other kind of micro data to discipline the model. And so we think it's very complementary because, we want to look at the effect of concentration. So having more firms, we want to look at the effect of changing this demand going beyond CAS. And so these are really two papers that you can look at together. And so finally, on the pass-through side, there's a lot of work on the static effect of market structure of oligopolistic competition in static models or permanent, where you look at the permanent effect of a cost shock happening to some subset of firms. And so there's a lot of work on that. And as I said, we're going to use this evidence to discipline our model for the macro. And so now I'm going to go to the setup, unless it's a good time to have some questions about, kind of the big picture. Otherwise, I can just go on and present the setup. Okay, so let's continue. So as I said, households are very simple. They value consumption, labor, and money. Firms, we're going to have a continuum of sectors. So that's standard, but within each sector, we're going to change the number of firms. There's going to be only a finite number of firms that can be any number n. And in each sector, you're going to have this Calvo price rigidity, so a constant probability of price change lambda. And the concept for the oligopoly game, so whenever you study these strategic, game theoretic interactions, you need to come up with you need to pick an equilibrium solution concept. So we're going to go with Markov, which is right now the dominant concept in IO, which puts more restrictions than just perfect equilibria where you can have trigger strategies and fork theorems. So we're going to go with Markov, and so here's the picture. Yes.
One short question. So the continuum of sectors is going to be important to make things tractable, right? So everything that you're going to talk about is going to be strategic interactions of firms within a sector. So all sort of effects between sectors of monetary policy are going to be shut down or not?
They're not going to be exactly shut down. So I will have something to say about that. but there won't be like strategic interactions between sectors. That's true. I think we can generalize our model. Like it's really, I think once you know how to solve the within sector stuff, you can generalize to between sector. It's just that it was easier, more transparent to do it that way. So you just have to use exactly the same thing twice, you know. But we think the main strategic interactions in the economy are still at the sectoral level. Now, what I call in sectors here, you can think of industries. Another way to view it is by regions, and so you could think of different regions where that's where the strategic interactions are taking place. But yeah, for now, it's going to be more tractable that way. It's going to provide us simple formulas, but you can definitely generalize to a finite number of sectors too.
Yeah, I was thinking more like, if you take these big firms that are usually in the sort of public debate about sort of increasing concentration, like, Apple, Facebook, Amazon, and so on, instead of being like kind of multi-sector firms in some sense, that they provide sort of services and goods in multiple sectors. So maybe if all the strategic interaction is going through those big firms, then it's not only within sector variation.
Yes, yeah, that's true. So, I mean, some of these big firms like Walmart, you still count them as retail, and some of them are doing different things. Amazon is still mostly retail. But even though a very large firm becomes large in different sectors, it can be accommodated in our model by just saying it's going to affect what exactly is the right measure of concentration to want to correct for it. But you could think of different divisions of the firms, of this large firm as different firms. It's going to affect the total profits of the firm, but here, since there's a rep agent, the single agent is getting all the profits, so that doesn't really matter. We don't have distributional issues. So it's going to affect a bit the total profit, but you could break it down by different divisions and think of these divisions as being large in their own sector, and that's what's going to matter. Now, it's true that there could be like more subtle forces saying, okay, I'm in two sectors. In each sector, I'm large. I'm going to do something, some kind of cross subsidies that allow me to make even more profit by pricing that way in that sector, that way in the sector. And this is something that we haven't modeled yet, but I think using the same methodology, machinery, we can do that.
So this is Ernesto Pastel. I want to do a brief comment here. If the definition of sectors here is more stringent than just industries or geographical areas, because you require that all firms within that sector are going to have the same degree of price stickiness, which may not be true in a given industry, no matter how fine the segregation you're looking at, or the same thing for geographical regions.
That's true, yeah.
Another quick comment is that I am curious to see how you're going to aggregate at the sectoral level, given that you cannot do the Calvo trick of aggregation because you have a finite number of firms in each sector.
Yeah, so for the first question, yeah, that's true. So now I'm not doing this, but we can allow for heterogeneity in price stickiness. So we have some results that I'm not going to show today that allow for some kind of heterogeneity within sector in terms of cost, in terms of productivity, in terms of stickiness. And so you could take care of that. For the second question, yeah, you're right. So what's happening, I think what you mean by the Calvo trick is a sort of law of large numbers. So different firms are hit by the Calvo theory at different time, but you can kind of aggregate and have a deterministic path for what's happening to the aggregate price level if you have a lot of firms. So that's the law of large number that gives you, deterministic aggregate dynamics, even though at the individual level, individual firm level, it's really stochastic because for some realization of the Calvo theory, you get to adjust a lot. For some other realization, you don't. And so that's the tractability that we're using by having a continuum of sectors, because you have different sectors with different concentration, but we always assume, you have a mass, some positive mass of one kind of sector that allows you to do this law of large number across these. And so that's the trajectory. So to answer like even more fully Federico's question and combining it with yours, if we had a finite number of sectors and finite number of firms in each sector, so everything, you would just have a finite number of firms in the economy, and then you do Calvo, and then you don't have this law of large numbers. You just have to look at expected path. So now you need to average. You say on average it's going to look like this, but I'm averaging over the realization, and it could be that for some realization the Calvo theory is just hitting one sector and not all of them. So we abstract from that, and so that's why we're going to have deterministic aggregate dynamics, even though in each sector it's going to be stochastic. And so I'm going to show you exactly how the dynamics work, and then you can see really why it's stochastic and why we need to average out. Does it answer your question?
Yes, it does. Thanks.
Okay, great. Thank you. So going back to the setup here, so I hope you can see the pointer, but here the utility is over consumption, labor, and real money balances. And so aggregate consumption is this aggregator of sectoral consumptions. And so as I said, S here is between 0 and 1, there's a continuum. Now, each sectoral consumption basket is itself an aggregator of n differentiated goods produced by the n firms in the sector. So a sector S has n firms, or NS, and so they each produce a different variety, and you aggregate these. And so we can do a lot just with this very general structure, having homothetic aggregator. I'm going to specialize this to what you see on the right, because it gives clean, nice formulas for the talk. And so we're going to follow the Gorosov functional forms that are common in the monetary literature, where you have log over consumption, log over real money balances, and linear disutility of labor. But this is really to get this nice formula for the transitional dynamics, where the weight jumps right away, the nominal interest rate jumps right away. When we do the Phillips curve, we generalize all this, and so we don't really need this for the last section. Consumption, we're going to use a Cobb-Douglas aggregator here across sectors. Again, this is not crucial. And within each sector, so that's what I meant by going beyond CS. The sectoral consumption basket is defined implicitly from the different n goods using this aggregator psi. So you see here that this is a Kimball aggregator, and a special case is when psi is a power function, then you get CS. And it's a power function that gives you the elasticity of substitution, but this is more general. Now the budget constraint is going to be, and here psi could depend on the sector too. I don't have a subscript, but psi should be thought of as psi s. Now the budget constraint is standard since you only have one consumer. So now on the firm side, each firm is going to produce this good I from labor only. So we don't have intermediate inputs or capital. Intermediate inputs have been shown to generate some neutrality in other papers, so we want to abstract from that. But of course, there are interactions between market power, what we described, and the input-output structure that would be interesting to consider. And so here, there's just labor, and so firms maximize this present value of profits, and the flow profit is going to be the amount that you sell, so this demand, times price minus your cost, which is just the wage here. And so the demand that firm I in sector A faces can be conveniently written in this form, where it's a product of something that only depends on aggregates. So aggregate consumption and price, aggregate nominal GDP, is going to act as an aggregate demand shifter. So firms get more demand when you have a boom. But then it's going to affect every sector in the same way. And what remains, and this is with Cobb-Douglas, otherwise with CS across sectors, you have a slightly different expression, but conceptually it's the same. You have an aggregate demand shifter times something that only depends on what happens within the sector. So that part D, we're going to call it like the sector demand function. But you should keep in mind that when you change, when you have monetary shocks and so on, you actually have two things going on, something at the aggregate level and something within each sector. And so within each sector is going to depend on all these end prices. So that can be a very large state space if you have a lot of firms. And so firms are going to maximize this by setting prices, so à la Bertrand, but subject to some Calvo friction, which is this lambda. And lambda can depend on S here. And so, and as I said, it could depend on the firm within the sector. And so the reset, when it gets to adjust, the important thing is the reset price that it's going to set. So that's the optimal price that the firm gets to set when it is hit by the Calvo flare. And so that is a concept that's familiar from the New Keynesian model, where you also have a reset price. And we know in the New Keynesian model that the reset price is really simple. It's just an average, basically, of future marginal cost, weighted, by the discount rate and the Poisson rate. So now here it's going to be much more complicated, because your reset price, when you get to reset, depends not only on calendar time, as in the standard New Keynesian model, and here calendar time encodes the path of aggregate variables, so wages, prices, aggregate consumption, interest rates, all these are encoded in this T, just to shorten the notation. But it also depends on all the other states, which are the prices of your rivals. So at any given point in time, you're the firm I that gets to adjust, and you look at the different n-1 prices of your competitors, and this is going to affect your strategy. You just don't look at your future marginal costs. While in the New Keynesian model, you only look at your future marginal costs. Okay? And so that's going to be the key object to understand what are these optimal strategies and how do they affect the transmission of monetary shocks to inflation. Okay? So now I won't describe the whole dynamic equilibrium and optimization program. Just focus on what happened in a steady state, because I think that gives enough of the idea of the structure of the model. So a steady state is, as usual, just constant allocation and prices. So that's the macro part, that's standard. And they're going to satisfy standard market clearing condition, optimality conditions for the household. The nominal rate is just going to be the discount rate. So we're looking at zero inflation steady state. But what's different is that around the steady state, you need to understand the behavior of these firms. And so think of a steady state, a macro steady state. So all these aggregates are constant, but so now you're boiled down to what's happening within the sector, which is an industry equilibrium, like in IO, like in Oppenheim, so like in more micro papers. So we're just focusing on what's happening within a sector because we take all the aggregates as given. But when I solve for the transmission of monetary shocks, I'm also going to take into account what's happening to aggregates. And so in a steady state, this is the Bellman equation, the HJ and the Hamilton-Jacobi-Bellman equation of the firm, where the value function here you have is the flow profit. So the sectoral demand that depends on the end prices in the sector, times P minus the wage, plus lambda. And here again, all the lambda is the same for firms, but you could generalize. And with this lambda, you're going to have a transition from V, the standard value, if all our prices are given by this vector P, to the case where firm J gets to adjust. So that's the new value function for my firm I, when firm J has adjusted its price. And J is going to adjust in a way that's optimal given the other prices. So this notation is to say all the prices except price J. So now my value function, the value function of any firm, like I, depends on the price of firm J, which has adjusted to this optimal reset price, and the other prices, not J, that have not been adjusted. So they're the same as in the vector P. They're sticky. And so you have these different transitions. And so each firm, here we're considering a symmetric steady state, and we generalize to non-symmetric, but here think of each firm as playing the same strategy because they're symmetric, and so the optimal reset price is going to be the argmax, is going to maximize this value function. So when firm I gets to adjust, it's going to solve this, as set the price that maximizes this value function. And now each firm J is going to play a similar thing, and so this J this G, the strategy G is going to be the same for J in the symmetric equilibrium, and so that's why we get this value function. So that's the hard part that we need to solve, which is this Markov game, where the strategy depends on the value. So that's where we're gonna bring something new. And so now, if you think of the steady state price vector, symmetric again, just going to be a fixed point of this, where the price played by each firm is equal to the best response to the other prices when they're the same. So everybody responds with P to the same price P. Okay, so does the steady state description make sense?
Yes. So this is Ernesto Pastén again.
Yes.
So from this expression, you can see that having the same lambda for everyone is important, because you can have basically you have to solve only one fixed problem on the pi and the p minus I. But if lambda is going to be heterogeneous for subset of firms, so basically here you can still use the lower large numbers, because even if firms have different characteristics, they all have the same probability of changing prices, and there is an infinite number of firms in the economy.
So here I'm just focusing on one sector. So here in the sector, there's only a finite number of firms actually. So there's not really law of large numbers. Law of large numbers is going to come once I aggregate across all these sectors and get the aggregate price level. But I think what you're saying is that if this lambda were lambda j, so depending on the firm, then I just have to put it back into the sum, right? I cannot have it outside. But it means that each firm is going to really have a different strategy. They cannot be symmetric anymore. So these G are going to depend on J now, because J has its lambda J, Gj, and then this would be Gi that maximizes this Vi. So or here I don't have this superscript because it's symmetric, and so we can solve for some. We can allow for some heterogeneity like this. So in the paper, we don't have it for heterogeneous lambda. We have it for heterogeneous demand functions and costs. But the way to solve it is similar for different lambdas. So we can consider the case where you have different GJs. And so then the steady state price vector is not just one equation, it's a system where Pi is the best response Gi to all the other Pjs. And each firm I is doing this optimally. But I'm going to come back to heterogeneity in lambda once I talk about different sectors. So I'm going to allow for some heterogeneity across sectors, and you're going to see that it actually amplifies what we're talking about. So in line with other work on heterogeneity of frequency of price change that amplifies, we're going to have this too, but coming from a different force, coming from something that's specific to oligopoly.
Strictly speaking, you don't need to, because you're going to talk about market power and not about heterogeneity in the lambda.
Sorry,
but,
what?
Strictly speaking, you don't need to, because you're going to talk about market power and not about heterogeneity in the lambda.
Yes, yeah. For most of the talk, I'm going to focus on market power, not heterogeneity in lambda. So heterogeneity in concentration, for instance. But I have one slide, if I have time, where I show you the interaction. Because empirically, there is an interaction between market power and frequency of price change. We don't endogenize it. It can come from menu cost models, but taking this as given, this generates some interaction.
Okay, great, thanks.
So just to understand graphically what's happening with this transition and these stochastic dynamics that I mentioned that happen within the sector. Here, so the x-axis is the price of my rival. Think of a sector with two firms. So there's I and there's minus I, which is the other firm. And so now the strategy of firm I is this G function that just tells me when I get to reset my price, what am I going to set given the current price of my rival. So if my rival has a price here, I'm going to jump to the corresponding point on the y-axis given by the orange line. So starting, And so the steady state is going to be the intersection of that line with the 45-degree line, saying that if we're at this point, then nobody wants to, when they get to adjust, they don't re-optimize because they're happy with their choice. So now what a monetary shock is going to do is push you away from a steady state. So because you have a monetary shock, in the long run, money is neutral. In the short run, prices are sticky or given by the past. And so you're not at the new steady state for nominal prices. You have to converge back to that. And so monetary shock pushes you away from the steady state. So suppose you have an increase in money supply, the new steady state price is going to increase by 1% if money supply has increased by 1%. But it means that our prices are now 1% away from the steady state. And so we are here. And so nothing happens until firm I gets to adjust. And then when it does, it's going to jump to here, to this point given by the orange line. Now, if firm I gets an opportunity again, it's not going to do anything again until firm minus I gets to adjust, because the best response has not changed. So nothing's going to happen until the other firm now gets to adjust. When the other firm gets to adjust, well, it's going to look at what is the price of firm I at this time. So the price of firm I is given by, you project this on the 45-degree line, and so it gives you this point. And so now firm J, firm minus I, is going to jump to this new price here, and then nothing happens until firm I gets to adjust, and so on. So in the end, they end up adjusting one by one. If you have two firms, if you have more firms, it's just that a firm never adjusts like twice in a row if others haven't adjusted. So you get a sort of alternative game, but it's stochastic. And so it could be that it takes a long time before one of the firms gets to adjust, while the other one is lucky, but nothing happens. And so eventually they're going to come back together to the steady state. And so you see that the speed at which they do that is going to depend on the slope of that line, that orange line. Because if that orange line is really flat, which is the standard New-Keynesian model of monopolistic competition, when we get to adjust, we jump immediately very close to the new steady state. And so there is some stickiness coming from the fact that, well, we have to wait for the Calvo adjustment to happen, but otherwise there's no endogenous, rigidity coming from the fact that, oh, we don't want to adjust too much because the other one hasn't adjusted yet. While here, it's going to be crucial. The slope is going to tell us how quickly we go there. Okay. Now, I'm going to present the first sets of results on sufficient statistics. So starting at a steady state, we do this experiment I just explained. There's an anticipated permanent shock to money and to nominal GDP equivalently. So at time 0, the money supply jumps to this new green line. And so what's happening? Well, it's continuous time, so you don't have an impact effect on the price. The price is continuous. But eventually, the price in orange is going to converge to the new steady state, the higher price level, because there's more money in the system now. Now, while the price hasn't converged, it means that consumption is higher than its actual level, steady state level, because nominal GDP has to be higher. And so you see that this is the dynamic. Consumption jumps, and it decays back slowly to the steady state. And so the faster the price level jump goes back to the steady state, the faster consumption is going to go back to its steady state, and the smaller the real effect of monetary policy. So a slower convergence means larger real effects. And so we have this formula. So here it's approximative because it's to first order for small monetary shocks. That's the dynamics of the aggregate price level around the steady state. So you have this money shock, and this tells you how the price level converges back to its steady state, to the new steady state, meaning it tells you the speed of the convergence of the real GDP to its steady state. And so it tells you the real effects of monetary policy. And so it's going to be a sum expenditure weighted. So here expenditure shares across sectors. So here, suppose sectors only differ in N, in the sense that conditional concentration, this is a simplification. As I said, we can generalize, but conditional concentration, they have the same lambda and demand functions and so on and cost. And so you're going to have these exponentials that decay at a speed that is not just the mechanical decay that you have in the standard New-Keynesian model, even with heterogeneity, where you decay just according to the frequency of price change. So you have to wait for the firms to update. Now it's going to be modified by these slopes. These slopes beta. Beta is the slope of these reaction functions, these strategies G, around the steady state. And so you see that a higher slope, higher beta, is going to act as if you had a lower lambda, which means that you have more stickiness. So higher slope is going to increase non-neutrality. It's going to make the conversion slower. And so we're going to capture, often talk as a way to summarize this. There are many ways. You can look at the cumulative output effect. They're all linked together easily. We're going to look at the half-life, which is when these two things cross, you know. And so the half-life is given by this time. And so if this is large, it means that the convergence is very slow. It means that you have a large effect of the monetary shock. Now, it can be large because the half-life can be large, so the convergence can be slow, either because lambda is really low, just in the standard thing, you have a lot of stickiness, it takes a lot of time, or because these slopes are high. And these slopes, we're going to show that they're higher when you have more concentrations. So we want to look at how these things vary with n and other parameters. Okay, so that's the formula. Now, so it tells you everything just depends on these slopes. And so, as I said, if the slope is very steep, a large beta, a large slope, it's going to be slow. Think of a very steep, close to the 45-degree line, it's going to be a huge amount of time, because every time a firm gets to adjust, it just sets a price really close to its rival. And then its rival gets to adjust, it doesn't move much either. And so it takes a lot of time to go back, because they basically don't want to depart from the other firm for many reasons, strategic reasons, demand, elasticity reasons, and so on. Okay? So now what we need to understand to really have a formula for that is what are these slopes? So I'm going to show you a formula that gives us these slopes as a function of micro objects. But just to give you another graphical depiction of the convergence process, just a different way to view it, with monopolistic competition and CS demand, the price after monetary shock, I want to set my price equals to the markup times the nominal cost. And so the nominal cost has jumped. So the nominal wage has jumped. And I have these markups. And so what I mean by there's a mechanical stickiness is that when firm I gets to adjust, it jumps to the new steady state, but it has taken some time and so on. Firm J gets to adjust, it goes to the new steady state and so on. So they always jump directly to the steady state. It's like the reaction function is flat. And still you get some non-neutrality coming from the fact that you have to wait for them to adjust. Now in the duopoly model, so you have a different markup that typically is higher, but they also want to go to their markup eventually, and that's what's going to happen when in the long run. But in the short run, firm I gets to adjust, it doesn't jump right away all the way. It stays close to firm 2's price. So it kind of wants to target a bit of a weighted average of firm 2's price and its marginal cost, and so on. And firm 2 is going to do the same, so it's going to be slower for that reason. Now, there are many things going on here. It's not just a real rigidity model where you have this variable elasticity of demand, so variable markups, and so you want to do something like this. These Kimball demands, even under monopolistic competition, can generate a slower adjustment. But here you have some sort of that, plus the feature that when firm 1 gets to adjust its price, it's going to think about, oh, now I have to act smartly because the price I set now is going to act as a state variable for firm 2 in the future. So like I'm Apple and Samsung, I get to adjust or BMW and Mercedes get to adjust. Now the price, when the other firm is going to think about adjusting, so either Calvo or because of they are gathering some information or whatever your theory of why they adjust, they're going to look at my price today and they're going to react, and this is going to affect how much they adjust themselves. And then how much they adjust at that time is going to affect what I do in the future and so on. So that becomes a very complicated fixed point problem that firms have to think about, which is the whole game theoretic part of the model. So now we want to understand this beta, these slopes, weighted by the number of rivals that you have, because that's what's entering the formula for the aggregate response. And so we have this, so we were surprised to get such a simple formula that tells you the slopes as a function of very simple statistics. So it's going to depend on lambda and so on, but that you can think of being close to 1 because the discount rate typically is smaller than the frequency of price change. And so it's going to depend on the number of firms, the elasticity of demand. So this is the elasticity of sectoral demand of this function D, evaluated at the steady state, and the markup at the steady state. So I need to know some steady state objects, which are elasticity and markup. And I could estimate them potentially using some micro shocks that don't interact with what happened on the macro level. So if I observe this, then I'm done, Even though there are many things going on, as I explained in the model, there are many things firms have to think about what's going to happen in the future when they set their price and their rival gets to reoptimize and so on. But all this is going to be encoded. We don't need to solve the whole model. We just need to see what the markup is, what the steady state markup is. So these are steady state objects that we see, and then based on them, we can infer what's happening in the transition. So these two things, transition and steady state, are not disconnected. They have a very tight link, which is what surprised us, that it would come up so simple. And so what's the intuition behind that? The intuition, I think the way to view it is reverse causality. Here, it's a symmetric game between the firms in the sector, so all these beta are the same. And so when I talk about it, I talk about, oh, what's my firm's beta? But what's really mattering is what is my rival's firm beta. So my rival can have a high slope or a low slope. If suppose in the extreme that my rival doesn't react at all to my price. So then I'm like in a static problem because nothing's going to happen in the future, or I'm in the standard case of monopolistic competition. Basically, I take their behavior as given. They're going to play something, but they don't react to my price setting. So I'm going to go for the Nash markup because there's no way, things are closer or exactly at Nash, and there's no like Stackerberg like element where by playing my price, I can manipulate what they do in the future. So the markup in the case of zero slope by my rival, my optimal markup is just going to be the Nash and just maximize my profit. Now, if they have a high slope, means that they're going to mimic me when they get to adjust. And so if I set a high price, they're going to also go higher. If it's low price, they're going to be lower. And so this means that we can together sustain a higher markup because we're not going to enter this thing where, if I set a high price where they don't care, they just price at their Nash markup. And so there's no reason for me to do that. And so a higher slope is going to generate these higher steady state markups. But now, how the formula works is now, I don't see the slopes because for the slopes are what enters the transitional dynamics formula for the aggregate price. So I don't see that. I want to know what the monetary shock does, but I see the markups. And the markups, a high markup tells me that the slopes are going to be high. So the convergence is going to be slow. Because the only way conditional on the elasticity and concentration to sustain these high markups is to have these high slopes, these high complementarities. Okay? So that's why if I observe the elasticity and the markup, I know the slope. Now, it's very important that I also need to control for the elasticity. Usually, in all the other models, basically, we're used to think of the markup being just elasticity over elasticity minus 1. And then maybe oligopoly changes what is the elasticity. So when you have fewer firms, the elasticity is lower because the residual demand is less elastic. But we think of that as just telling you what the markup is going to be. Now here, you see that they enter independently. And so it means that conditional on the elasticity, there are actually sources of variations in markups that are not just demand elasticities and that are not just concentration. Why? Because it's a dynamic model, so many things affect the markup. I'm going to show you a picture, like the frequency of price changes affect the markup, and higher order of properties of demand affects markups. So the markups depends on super elasticities of demand, for instance. And so now the beauty of that formula is that you don't need to know all the factors that determine the markup. You just need to see the markup. And that's going to act as a sufficient statistic for all these other forces that may affect the markup but are hard to solve for. Okay? And so the formula here is controlling for elasticity and concentration. A higher markup means a higher slope. And so in the cross-section, you could think of regressing the non-neutrality, for instance, sectoral or regional cumulative output effects responding to monetary shocks as a function of these different things. So frequency of price change, but concentration, elasticity, and markup. And you would find a positive relationship. Was there a question or? Yeah.
Yes, there is a quick question. I'm a little surprised of calling this multiplication between the elasticity and the markup sufficient statistics, because you also need to know n, and in some extent you need to know rho and lambda. And for instance, think about n, the concentration, may not be that easy to measure if you think that these firms are going to be complicated objects with probably many products, many locations. So it's not going to be so easy to isolate concentration within sectors in the way that are defined here.
Yeah, that's true. Yeah. So, well, sufficient statistics should have an S here. So it's like you need different things. What I mean, I want to call it sufficient statistic because in the model there are many other parameters that don't appear here, and so they are encoded by the markup. Now it's true that you still need to know n and the elasticity, and so we think, yeah, maybe I should add a bullet point here, which is not markup observable, maybe, but also concentration observable. So you need the right measure. You're right. And so I think it goes back to this initial question of you have large firms in different sectors. You need to, a good question is what is the kind of interaction in terms of prices? What is the degree of aggregation that matters for the response to prices that matter for inflation? If you think of the CPI, so you decompose into different goods and different regions, and in each region, for each good, you need to come up with some measure of the concentration. And so I agree that empirically, that may be a challenge. Now we think, to first order, it's just going to be by sector. So you take the inverse Herfinder, for instance, in a sector, and that's going to give you a good measure of this effective number from n. But I agree, it's a good question. And I'm going to come back to that briefly, actually, saying because empirically, the striking fact in the US is that the concentration at the aggregate level in many sectors is rising. So if you look at, just at the US as a whole, but at the local level, that's been shown by, Daniel Stapp, Nicolas Trachter, and Esteban Rossi-Hensler. If you look at more granular levels, focusing on the same industries, you see that concentration has actually fallen if you go very local. And why is that? It's driven by the same thing, which is not necessarily that firms are in different sectors, but just focusing on a single sector. If, say, retail, now you have Amazon or Walmart growing, so they're going to get a larger market share at the national level, so concentration is going to rise at the national level. And then at the local level, they're going to enter and compete with the local firms, and so concentration is going to fall at the local level, actually. And so there's a good question, and we haven't taken a stand yet on that. Like, I need to think more about it. What is the right measure here? I think it's going to be a combination of industry and region, but it's partly an empirical question. What are the determinants of aggregate inflation? And so depending on this view, you could think that concentration rises or declines. What our model is saying is once you have the right measure of concentration, it's going to amplify the effect of monetary policy. Because of that. Note that in this formula, once I control for elasticity and markup, if I increase n, it's actually increasing the slope. So it seems to go against what I'm saying, that concentration is amplifying. But the thing is, when I say concentration is amplifying, it's because the effect that concentration has on the markup is actually going to be stronger than this direct effect of n. But we can come back to that later. And so just to come back one last time to this graph, think of two sectors or two like counterfactual words. That is the link between markups and slopes, controlling for everything else. So controlling for frequency of price change, number of firms, elasticities. If I have a higher markup, higher price in the steady state, then I know that it has to be sustained by a steeper slope, meaning that economy is going to react slower. The price level is going to adjust more slowly to a monetary shock, and so you're going to have larger real effects, more non-neutrality. So now, as I said, if you know how these things evolve over time, or you just have a snapshot, this tells you what you need to know, but we may not have that detailed estimate. So we're going to go now more structural, do comparative statics, counterfactuals when solving the model. So any question here on the first part, or it's clear?
So Olivier, can you allow for heterogeneity in, say, productivity at the firm level within sectors?
Yes. So I'm not showing them because the formulas are a bit more complex, but we can allow for that. So because we do think that in each sector you have large and small firms. So we allow for that. It's just that it's more complicated because, as I said, when I was talking about heterogeneous frequency of price change, when you're going to have different betas for different types, like small firms are going to have a beta, large firms are going to have a beta, and then you have even more betas, which is how small firms may respond differently to a large firm price change than to a small firm price change. Maybe they don't care about other small. So it's a whole, it's a matrix version of that, basically. But it's more complex, so I don't have it here. But it's in the paper. So now I'm going to specialize a bit. Like everything we do is really non-parametric, just in terms of elasticity, superelasticities. But just to connect with the literature, I'm going to use this functional form for Kimball demand, which is from Clino and Willis, because it's what's most commonly used, where the elasticity is this parameter eta, and the superelasticity, which is the elasticity of the elasticity. So the idea is that, unlike in CS, your elasticity depends on your relative price. And so when you charge a higher price compared to people, demand becomes more elastic. So you don't want to do too much of it because you start losing a lot of customers. So you have these kind of log concave demand curves. And so that's parameterized by theta. So theta equals 0 corresponds to CS. But theta can be potentially really large, actually, if you try to match the pass-through estimate. Now, when you have a finite number of firms, elasticities and superelasticities are more complex expressions that also depend on n, and they are kind of entangled too, so it's not as cleanly separated, and we describe it in the paper. But the point of that is to say that also, even with CS, when you have a finite number of firms, because the residual demand is not going to be log linear, it's going to be somewhat log concave. And so you have some positive superelasticity in the CS case when you have 2 firms, 3 firms that you wouldn't have with an infinite number of firms. And so having a smaller number of firms acts partly as increasing the superelasticity. And so that's why we really want to, allow for non-CS demands to really control for these different factors. Now, I mentioned that briefly, that under monopolistic competition or static models of oligopoly. So basically all the models that are out there, except this very specific dynamic oligopoly models, the markup is very simple. It only depends on the elasticity. It's the Lerner formula, elasticity over elasticity minus 1. Now, in this dynamic oligopoly context, and in fact, the reason why the theoretical IO literature came up with dynamic oligopoly models initially, like Bertrand Maskintiol, is to solve the paradox that comes from that, like the Bertrand Paradox, which says that you go to marginal cost if the products become very substitutable. If you play static Bertrand, you don't have this in Kono, but in Bertrand, they make no profits if they have perfect substitutes. And so partly this IO literature has developed to answer that question, which is where the markup doesn't only depend in the simple way on the elasticity. And so in our model, it depends on the elasticity for sure, but also many other things. Even controlling for the elasticity still depends on the number of firms. It depends on the superelasticity parameter theta, which is very unique to that model because, in monopolistic competition, a model with real rigidities in the way of the Kimball demand, you do have like amplification of monetary policy, but this is unrelated to the markup. And so it's like a free parameter that you cannot tie to concentration, that you cannot, look at in the cross-section, whether more concentrated sectors react by more and so on. It's just another parameter that we typically set to 10, like in Metz-Wouters, but here, it's tied to the microstructure. And so that affects, and here it's going to affect the markup. So you can infer something as I explained. And it also depends on the frequency of price change. So the effects are not large if you think of just like the absolute effect on the markups. For instance, here I'm increasing theta from 0 in CS to 10. I have 3 firms, so you go from 0.18 to 0.2. But what matters for the formulas then is markup minus 1. Remember? So then the effects can be potentially large for the half-life, for the slopes. And similarly, if you increase the frequency of price change, you actually increase the markup. But if you have a lot of firms, then you almost get no effect. N equals 20 here in blue. You see that. So there's an interaction between the number of firms, concentration, and these effects on the markup coming from the frequency of price change. Sorry. Okay, so this is just to remind you that the model generates variation in markups that's richer than in other models. Now, let's go to the half-life, which is our main object of interest. How does that vary with the number of firms? So we're going to start with this benchmark, which is a CS economy, theta equals 0. And you see that when you have 2 firms, you have some sizable amplification. So think of 1 as the case of the standard New-Keynesian model. So monopolistic competition, CS, in fact, and so the half-life is just driven by lambda. You have lower lambda, more monetary non-neutrality, so we're normalizing by that. And now, if you have 2 firms, you're going to get 40% more. So it's pretty big, but it kind of decays very quickly with the number of firms. So think of reasonable measures of concentration tell you have like 10 firms, 15 firms, so you're in this range. And so there you're already really close to the standard model. So oligopoly has some big effect when you have 2, 3 firms, but not much beyond that. Now, this is very specific to CS. And in fact, think of these models that are parameterized to match like higher superelasticities, 10 or 15. Then first, you can have a large variation, but also note that it's not a given that concentration is going to amplify the effect of monetary policy. So in the CS case, higher concentration, lower N, is amplifying this. You get from 1 to 1.4. Now, if you have high enough superelasticity, it's the other way around. Concentration is going to dampen. And why is this happening is because of formulas that I'm not showing here. it's because how actual superelasticities depend on not only parameters like eta and theta, but also on n, and the way they vary with n depends on theta. But what I want to say is that so now a key parameter when you look at this is what is actually theta, what is theta n, so what is the superelasticity in different sectors. And so there's no clear guidance on that a priori, but the one we're going to use is estimates for idiosyncratic cost pass-through. So we know from other models like Atkinson, Borstein, and others that pass-through depends on market structure, and in fact, so this is the most recent version of this line of this literature, which is that pass-through is very heterogeneous across the firm size distribution. So small firms behave very much like in the constant market case. They have high pass-through. They pass through their cost shocks one for one. And here I'm talking about the pass-through of an idiosyncratic cost shocks. So I'm a firm, my cost changes, for instance, because of an exchange rate change. And my rivals' cost, I control for my rivals' cost and prices. So these are holding this fixed. What am I going to do with my price? Small firms are going to pass through their cost one for one, roughly. Large firms are going to pass it through much less. Maybe 50% is going to be an increase in the price if my cost has increased. But then the remainder, the 50%, is going to go to the markup, right? Because my cost has increased by more than my price. So my markup is going to shrink if I'm a large firm. And so they show that this is consistent with CS, Gournot, but not Bertrand. In fact, that's because they stick to CS. And so what we do here, because we have to go with Bertrand, which is the dynamic price setting game, in fact, that can be completely consistent with Bertrand as long as you depart from CS. And so we're going to use this Kimball demand to match this evidence of pass-through as a function of market share, okay? So different sectors or different firms have different market shares and they have different pass-through. So I can compute the pass-through to an idiosyncratic cost shock in the model, in the dynamic model, back this out. So it's a form of indirect inference. And, find the theta parameter that allows me to match that. And this is going to give me how theta varies. So theta is not going to be like 0 or 10. It's going to be something that depends on the market share as well. And
Olivier?
Yeah.
This is Ernesto Pastel again. A quick clarification. So this evidence that you're showing us here from Amites, Corky, and Conning is based on cost shocks idiosyncratic or aggregate?
It's so they have very detailed data in Belgium, and the shocks are exchange rate shocks. So we look at Belgian, say, exporters, or a Belgian firm, or any kind of Belgian firm that imports some inputs from abroad, and the exchange rate shock is going to change the cost of these inputs. So to
some extent, it's more heterogeneous. The effect of the shock is more idiosyncratic. It has a strong idiosyncratic component.
Exactly.
That a monetary policy shock within the context of the model you study.
Exactly. So the monetary shock affects all the firms. Well, how much they import doesn't matter. It affects everyone through the wage. The exchange rate shock affects firms differently, depend on their import intensity and so on. And so
I think interaction is important. Evidence of pass-through coming from cost shocks that are idiosyncratic may not have a one-to-one interpretation to cost shocks that are aggregate.
Exactly, yes. And so we don't use a one-to-one interpretation. I use the model to look at two things. I do idiosyncratic cost shocks in the model, look at how these firms pass them through to their prices. This gives me a measure in the model of idiosyncratic cost pass-through, and this matches the evidence of the literature on idiosyncratic cost shocks. And then this disciplines my estimate of theta. This allows me to calibrate the model to then look at what happens to an aggregate cost shock like monetary shock. But it's not done directly. You have to do it's a sort of indirect inference or to calibrate the model. So there are like two steps. Thanks for yeah.
Olivier, just to remind you that you have 15 minutes.
Okay, great. So what do we see? Like, just to show you a bit why CS is not doing a good job and why a fixed high theta parameter is not doing a good job either. When this is passed through as a function of market share, and CS basically with Bertrand tells you that the pass-through doesn't decline fast enough. So it's true that small firms with zero market share pass through 1-for-1, but large firms like with a 30% market share, CS predicts that they pass through only like 80%, while in reality it's much closer to like 30% or. And so I'm going to target this black line, which is a pass-through that declines quickly with market share. And if you had theta equals 10, it wouldn't work either. The pass-through would be lower for everybody, even the small firms. So that's not good either. So we need something. We need a theta that depends on the market share too. And the way to view it is just that the Klenow-Willis functional form is not the right one if you really think of heterogeneity within sector and so on. So you could back up a very non-parametric Kimball aggregator that engineers that. We're just going to do it through variable theta, but everything is in fact non-parametric. And just to finish on this, the rest, I'm still going to assume like symmetric number of firms. So here, so when I vary the market share, I'm actually varying the number of firms. Let's say you have 3 firms, so each firm has a 33% market share, their pass-through is here. You have 5 firms, each firm has a 20% market share, their pass-through is here. Now, in reality, this evidence is for different firms that operate in the same sector, they're heterogeneous. You have some small, some large firms. And so it's not like symmetric. But we show in the paper that it doesn't make a difference. Once we do the whole procedure where we allow for heterogeneity in productivity within the sector, as when I answered Federico, and then I get large and small firms within a sector, and I vary the market share of large firms, we get similar. It doesn't affect the calibration. And why? The intuition is that in static models, market share is actually a sufficient statistic for a pass-through. You don't care whether it's coming from I'm a large firm facing a lot of small firms, or I'm a large firm facing other large firms. In a static model, you can show analytically that it gives you exactly the same pass-through. So it doesn't matter. In the dynamic model, it's not exact, but it's very, very close numerically. And so once we do that, what do we find? So this would be a headline number where I'm varying the market share in the economy from, say, 0 is the standard monopolistic. So again, I'm normalizing the half-life to 1 in that case. And I'm showing you that concentration increases. If concentration increases, so you go to the right, the half-life increases. And so if you think of a crazy world where we went to just 4 firms in the whole economy, in each sector, like just Apple, Amazon, Facebook, Google, you just had 4 firms, pretty symmetric. The market, the Herfindahl would be like here. And this would double the effects of monetary shocks just because they would be very careful about their price setting due to their rivals. Now, in reality, we're not concentration has increased, but not that much, So we went, if you look at national concentration, we went to around here, 5%, so effective number of firms of 20 to maybe 10. And so if that's the number that's relevant, monetary policy has become 15% stronger. Now, if it's local concentration, then we actually went from 0.15 to 0.05. And so again, for now, we're not taking a stand on which measure is the most relevant one. It's partly an empirical question, but this tells you if concentration increases, that's what's happening. Okay. Now, briefly on heterogeneity in lambda, where you have heterogeneity across sectors, you can see that the cumulative output effect, so basically like the half-life that I mentioned, that's larger when it's larger, you have more non-neutrality. It's going to be given by this formula. So you take the average duration across sector and the average, this factor, which is the slope of the half-life in a sector as a function of the duration. So here I'm showing different sectors, n equals 3, very concentrated sector in blue, n equals 20, less concentrated. And so this gives me the slope from the formulas that we had. But then you have a covariance term. And so I understood that this comes back a bit to your question. The covariance term says that if you have a positive covariance, meaning that concentrated sectors, for instance, that have a high slope here, meaning a high 1 over 1 minus the slope, if they also have a higher duration, so more stickiness, lower frequency, then this is going to amplify. And there isn't much evidence on that. Simon-Mungy has some evidence with scanner data that shows positive covariance. And there are other, indirectly, there are papers that show that, the frequency of price change is lower when pass-through is lower. So overall, we have a consistent picture, we think, where in concentrated sectors, you have lower pass-through, lower frequency of price change, these higher slopes, and so you have this positive covariance. And the intuition is that, well, if you are very concentrated sector, so very high slope, but you adjust a lot, well, it's kind of, you're wasting this stickiness on the sector because it's going to adjust a lot anyway. So things are amplified if, the concentrated sectors are not adjusting a lot, because then they have a very slow conversion back to the steady state. And so they drive the aggregate price index is going to be moved slowly because of them. Okay, so now, okay, I have like 8 minutes, so let me go a bit quickly over that. So there are two things that happen when you change the number of firms. One, the firm cares about its competitors' prices. So we call that a feedback effect. It doesn't want to depart too much from competitors' prices. The second, there's a strategic effect where, because future firms are going to care about my price in the future, I can use that to manipulate their price and change my pricing today. And so these two things are playing out together. Now, the feedback effect is present even with infinite n monopolistic competition when you have intermediate input or when you have Kimball demand. And so we don't have intermediate inputs here, but we could think about that. We're going to construct an economy that has an infinite number of firms and has different demand functions, different Kimball preferences that match the elasticities and superelasticities of the oligopolistic model. So in reality, you have a finite number of firms that gives you some superelasticities and elasticities. Now we construct an as-if economy that has an infinite number of firms that matches the same elasticities. But to do that, well, since the number of firms is different, you need to change other parameters in the background that are not observable anyway, because the observable in real life are elasticities. And that as-if economy has an interpretation. It's actually the equilibrium if firms were behaving myopically, ignoring how they can affect the future pricing of competitors. So if they're myopic, like behavior, they're going to set, that's going to be the equilibrium. And when we disentangle, we find that for these permanent monetary shocks, under our calibration, this half-life tilde is the half-life that you get from that as-if economy. And so you see that the half-life that we get from the actual strategic economy is very close. It's like 4% higher when you have 3 firms, and then it decays quickly. Now, when you have a large number of firms, they have to all go to 1. But when you have a small number, you have some departure, but it's just like 4%. Now, it's still much, much higher than what we get under CS, but it's just 4%. Now, this tells you that to understand permanent monetary shock, you can understand a lot through the lens of this as-if economy, where you're just matching the superelasticities. Now, things are, it doesn't, the total effect is still very large. That's what I showed you. Concentration can still amplify a lot. the effect of monetary policy, but it's going to work a lot through that implied demand function. Now I'm going to conclude with this. So we want to generalize the model to allow for, because the monetary literature has looked at these permanent M shocks, money supply shocks. Now in the new Keynesian world, we're more used to thinking about interest rate shocks, real shocks, mapping whole path of shocks to path of inflation, not just a one-time thing. And we want to do that because we think it's important to embed into a richer model with the other equation, Taylor rule, and so on. And also because we want to investigate whether this near equivalence of the non-strategic economy with the strategic is specific to these shocks. And the answer it is. So I'm not going to show you the details, but the new Keynesian-Phillips curve is a higher order differential equation, not just first order. So we generate endogenous inflation persistence, and higher order persistence too. So it can go to up to order 7, not just the standard inflation persistent, which has the past and the current. So order 2. Inflation is going to depend not just on future marginal cost, but demand conditions, interest rates, and so now the Phillips curve is not going to be equivalent to a monopolistic Phillips curve with Kimball preferences, so real rigidities in the literature. So just to show you an example, suppose you have a standard new Keynesian-Phillips curve with our calibration that would be written this way. So it's a first order ODE. Now, if you had 3 firms in the economy, the Phillips curve we get is basically this. So you get higher discounting, much less reaction to marginal cost. So you go from 1 to 0.2. And these terms that are inflation persistence and endogenous cost push shocks. So if real marginal cost has some variation, it can act as a cost push shock generating inflation. But its macro-founded is coming from the fact that firms are behaving strategically. Now, a non-strategic Phillips curve, just doing everything I said, the as if economy would have this. So still low discounting, and that term is very close, the 0.2 and 0.17, but it doesn't match these other terms. And these other terms start making a difference when you consider richer shocks, not just the permanent M shocks that we looked at previously. And so that's our way to understand why is it so close in one case and why not, because the Phillips curve involves these richer things. Once you combine with the other equation and the Taylor, you do shocks, real shocks to the natural rate and monetary shocks. You generate big path. And so here I'm just going to look at the standard deviation of consumption over 100 years, 200 years with the simulation. And you see that a model with 10 firms, so pretty high concentration, but not crazy given the current amounts, in the MPE, which is the full model, is very close to micro-founding what people target in the DSG literature, which is monopolistic with high theta. So you see 1.1 versus 1, 1.4 versus 1.3. So we think it's much better because it's micro-founded in the market structure, and it gives you a lot of additional predictions relating markups to what's happening here. But there's also some meaningful departure with the non-strategic economy. So the non-strategic economy would overestimate the non-neutrality. And so, especially compared to what people have estimated in the DSG literature. So overall, let me conclude here. Monopolistic competition is used everywhere for good reasons. It's very tractable, but it may be a less and less good approximation as the economy evolves and concentration increases. And so we think it's important to understand how we can move beyond that, or there are meaningful departures, in particular for the macro experiments of monetary shocks. Showed you 4 sets of results. First, the mapping from the micro steady state objects, so markups in particular, to the macro transitional dynamics. Then I calibrated the model to match, idiosyncratic cost pass-through and its heterogeneity between across the firm size distribution. So that's very, recent evidence, and we think that's the best evidence that we need to target to understand how to calibrate this model. There are other ways in the price stickiness literature to calibrate models based on the frequency of price on the price change distribution. It's a very different strategy here, and it would be useful maybe to reconcile the two. And I may have something to say about that if you have questions. Now, for simple shocks, most of the effect of concentration of the amplification of non-neutrality is coming from what's happening to changes in residual demand as the number of firms decreases, rather than these strategic interactions that are very interesting in terms of like the theory, but maybe not as relevant for these shocks quantitatively. But they become more and more relevant when you go beyond these simple shocks and generalize our model to the Phillips curve and look at different paths because of what they do to inflation persistence and endogenous cost per shocks. Thank you.
Thank you, Olivier. I think we have time for maybe one or a couple of questions from the audience. So remember, if you have a question, please write in the Q&A section, and we're going to open the microphone for you.
I have a question in the meantime.
Yeah.
So thanks for the talk, Olivier. It's very insightful and interesting. So I have a question. I think it's kind of related to identification of this, because you're treating the sort of Calvo parameter. I mean, that's just a parameter, but then if you go to the data and sort of measure the frequency of price changes, you probably use those moments to sort of target that parameter. But then somehow in your theory, the frequency of price changes is sort of related to, like, if you were to take the simulated data from your model in terms of, how frequency price changes are occurring after monetary policy shock, that will be a function of the Calvo parameter, but also a function of concentration, as you were saying. But then there's the issue of identification. If you go to the data and you want to measure price frequency, you need to sort of adjust your Calvo parameter to take into account this mechanism to sort of get at the B parameter of the Calvo parameter relative to sort of the price changes that you see in the data. So in some sense, it feels like this is like another micro foundation for why firms are adjusting prices slowly as a response to shock. And then I guess I'm not sure if this is right, but your sort of the theory is sort of telling you that you need to take into account concentration when you want to estimate the Calvo parameter using frequency of price changes. Does that make sense?
So I think you have something a more general model in mind, which is not Calvo's, because if you have Calvo, then the frequency directly translates into the Calvo parameter.
Yeah.
But what concentration does, and everything I described, is more telling you what are the price changes when firms get to adjust. But it doesn't change their frequency. So the frequency are exogenous here. Now, I mentioned at some point that empirically, there is a relation between the frequency and concentration and things like this that you could microfound in a menu cost model. And people have done that, Gopinath and Ichkoki, for pass-through, for instance. But in our case, once you take them as given, it's directly revealed by the frequency of price change, the Calvo parameter. And so then the other things, when I say the firms adjust more slowly, it's not, they still have the same frequency, but they adjust more slowly because they're going to make like smaller changes. No, there is a thing I agree, which is that when I say there are two firms, if the other firm has not adjusted and I get to adjust, then I'm not going to adjust, even though I was hit by the Calvo ferry. And so that may be the bias that you have in mind. But I think that that's an extreme case where, I don't do anything if I get to adjust if the other firm has not adjusted. in reality, I still have had some idiosyncratic shocks in the meantime. And so I'm still going to adjust a little bit to that, just not a lot. And so it's not going to, as long as I adjust a little bit, you're going to see in the data a price change. And so you're not going to be underestimating the frequency.
Yeah, I guess I was thinking more like in the moment of price changes as a response to the shock, and not the unconditional sort of frequency of price changes. But I guess you're right that I guess when people sort of take these models to the data, they don't use the price response, but just the unconditional frequency of price changes to calibrate the Calvo parameter.
Yeah, they just code 0, 1, like whether it changes. Maybe you Winsorize a bit the very small price change. You're afraid it's a mistake, but otherwise it's just like, did you change? Now, talking about this, I mean, because it's true that in the monetary economics literature, and some of you have worked on this, like you target the price change distribution. That's the name of the game, to see whether you have selection effects. You look at kurtosis. Do you have a lot of small price change, or all these different things that people have worked on in the closed economy setting. And now what we're doing, we don't have idiosyncratic shocks, and we're targeting pass-through evidence of long-term cost shocks, and so that's very different. And now it seems. Now, one feature of the closed economy monetary literature is that you see a lot of large price changes, and presumably driven by large idiosyncratic shocks. And so that seems hard to reconcile with these strong rigidities that make you not want to depart from your competitors. And so that's been a problem for some models, like Klino-Willis, for instance, or Burstein-Helvig. They say real rigidities cannot at the same time give you like small reaction to aggregate shocks and large reaction to idiosyncratic shocks. But the thing is, these models have homogeneous firms. And once you think about like heterogeneity, it could well be that a lot of features of the price change distribution are driven by these many small firms that do behave, pass through fully, so have large price changes, don't seem very affected by all these forces I'm mentioning, even though the large firms are gonna not adjust by much, as in the theory, so display strong real rigidities, but the large firms are driving a lot of the aggregate price level because they have a large market share. So I think it could be very interesting to look at the price change distribution by market share, see whether you see the same patterns as the international literature on exchange rate pass-through, and maybe reconcile everything, because that would be a nice way.
Yeah, I guess you don't have a sense yet of how much of the effect of monetary policy shocks instead of cost shocks are sort of captured by sort of competition concerns and just standard price adjustment frictions. Right? That's sort of your take, that you would want to sort of decompose that using evidence on how monetary policy shocks are passed through to prices.
Yeah, well, I mean, really, when they target the price change distribution, they don't even condition on monetary shocks.
Yeah.
Look at the unconditional, and you see that there are a lot of large price changes, and so they have to come from idiosyncratic cost shocks or productivity shocks.